So welcome back to the afternoon session, everyone. And for this final lecture of a very interesting lecture series by Joswig from TU Berlin and MPI, MIS in Leipzig on optimization and tropical combinatorics. And today's lecture will be on product mix auctions. Over to you, Michael.
Thank you very much. Welcome back, everybody. Indeed, today I will talk about product mix auctions. And so this is a topic which brought tropical geometry at the forefront of applications in optimization and elsewhere a few years ago through some groundbreaking work of Baldwin and Klemperer. And I'm kind of reporting a little bit on their work in a version which was written up by Noctran and Josephine Yu. All right. So this topic in a way belongs to the area of operations research. So this you could see as the area where mathematical optimization gets applied to questions in economy. And so this is really a thriving subject. And so you should expect many, many interesting new results from this area soon. Actually, I'm currently working on some aspects of this, and I did already in the past. All right. So now, without further ado, so there are many, many, many auctions. And so these are just ways to distribute goods and money in certain ways, such that some amount of social welfare is maintained. And so the topic is sometimes also called mechanism design. And this is interesting for a number of reasons. For instance, so the big internet platforms like Facebook or Google, and so they make their money from advertising. And so the prices for their ads, so they are not constant price, but they are rather a function of a number of things. And so the prices are negotiated constantly through non-trivial algorithms. And so these kind of auctions, so these are implemented in this form. It doesn't necessarily need to be an auction of the kind that I'm talking about. But what I would like to convey is that these auctions are around you and every one of us all the time. All right. So the situation that we want to look at is the following. So we have M bidders, also called agents. And so they compete for combinations of several goods. Right. So I'll try to keep the parameters the same throughout the talk. So I have M bidders. And I have n types of goods, and the assumption is that these are indivisible. Right? So these are sold in numbers and not in. So there's no measurement. I cannot split up a good into two halves or something like that. So therefore, any combination of these goods is just a point in Z to the n. And so this is also called a good bundle. So please see that I'm allowing integer coefficients as well. And so this means that in this model, buyers and sellers play the same role, right? If you have a positive value, so then you demand a certain good. And if you have a negative one, then you intend to sell it. So now what is crucial to this model is every single buyer is allowed to have their own opinion on how valuable a particular good, or even more so, every bundle is, right? So it is not assumed here in this model so that the valuations are additive. So right, so it may happen that if I want to bid for good A and good B, so then these two are exchangeable to me. So then bidding, but I only need one. So bidding for the union of A and B, it does not necessarily incur the sum of the prices for A and B. Right, so this is what this model allows. So the valuations don't need to be additive. So I really pick each combination of goods that I like, and I set a number to that. Okay, so these are my valuations, and these are independent. So every bidder has their own valuation, and this J here and this U function U, so this is not a power, so this is an upper index. All right, and so this likewise, this is an upper index. So this is the common notation here in this business. Now I'm looking at the Minkowski sum. So I have m subsets of the z to the n, aj, and I take the Minkowski sum of all of these. So I get another set of integers in R to the n. So, and this is capital A. Now this comprises now all the combinations of good bundles for all these agents. Right, so this is the capital A, and so whenever you see an index J, so then this is the corresponding thing which only depends on agent J. So now, so what is the goal of this thing? So this mechanism design business is typically seen from the perspective of the auctioneer. So the auctioneer has the goods. They should be sold to the people, and then so the auctioneer in this model just fixes some kind of price, and after the price is fixed, the agent wants to maximize their profit. So let's see how this looks like in this model. So since we have n goods, a price is a vector in R to the n, and here it doesn't hurt to have real numbers, so they don't need to be integers. That doesn't play any role here. Now, the bundles that optimize the profit for everyone, so these form the so-called demand set. So this is a crucial notion in this setup. So let's look at the situation. So A is one of the points which is among the bundles that are interesting to agent J, right? So, and uj of A, so this is the value that agent J gives to this particular bundled A. Now, the profit that that agent gets from this particular bundle is just the personal valuation minus the price that they have to pay, right? So this is the price vector scalar multiple with A, right? And so in this profit should be maximized, and again this depends on the agent. So for a fixed price, the agent for that particular valuation function maximizes the utility, or so the profit at their demand set. So this is the thing. And now I'm looking at the aggregate valuation. So I put all the valuations of all the agents together. So this is the function capital U. So this is now the maximum total valuation taken over all ways to partition such a bundle. All right, so again, let's look what this looks like in this formula. So I take these valuations. So here the arguments are again bundles, and I take bundles from each of the sets AJ. I look at the valuation of the individual. So this is still the individual valuation for that particular bundle. I sum them up. So this, you could see, this is a measure of welfare, right? If this value is large, then many people are happy, right? So this is what the idea about this thing is. But of course, in order to make sense for my auction, I'm only interested in the situation where I'm looking at bundles which are actually of some value to the individual agents, and so where all the goods are actually distributed. This is the assumption. So you see, so in this auction, there's nothing like a leftover. So everything, I'm only interested in a situation where everything is sold or bought, right? So remember, negative values are allowed. Okay, so this is the aggregate valuation, which measures social welfare, if you, and so this maximizes social welfare. Now, and then, so now since I have an aggregate valuation, I also have an aggregate demand. So this is exactly the same formula as before, but I replace the individual uj for the agent j by this global function capital U. So, and then it is easy to see that the aggregate demand is just the Minkowski sum of the individual demand sets. And this is the situation. Okay, now, so we'll see an example in a minute, but so there's one thing which is particularly important, and this is kind of the key notion in this entire game. So this is competitive equilibrium. So what is this? So let A be a bundle. So this is just one of the lattice points. So just some linear combination, integer linear combination of goods. And so competitive equilibrium exists at that point if there is some price such that the particular bundle A is in the aggregate demand for that given price. Okay, let's go back. I know, so it's a lot of notation and there's a lot of notions, so let's do this slow. So the situation that we're looking at is this: the auctioneer fixes the price P, right? So then the prices lead to, so the order of the history of the game is the following. So the agents have their valuations. They can be even secret, so it doesn't matter. And then the auctioneer fixes a price. Then we have the individual demand sets, the aggregate valuation, and the aggregate demand, right? So this is social welfare type of thing. And now the equilibrium exists at a point A if that social welfare is attained for that given price. Okay, so that's a competitive equilibrium is a desirable situation from a social welfare point of view. That's the idea. Okay, so this means that the price is chosen in a way that such that all agents simultaneously are happy, which means they maximize their profit. Right, so that's why it's a good thing for everybody. All right, so now how is this related to tropical geometry? Well, and if you see this here, so essentially you see this maximum of this thing over here. So this is essentially a tropical polynomial. But now let's make this precise. So the valuation function of fixed agent J. So this defines an n-variate max tropical polynomial. So again, we are in the max world, so which is common in optimization. And I already explained some while ago why this is the case. Well, so this is because of the order preserving property of the valuation map in this. So here's a terrible thing. So in the economics literature, these functions of the agents, so these are called valuations, and in tropical geometry, we also call the function that maps a Puiseux series to its lowest order term a valuation. So this is unfortunate but unavoidable. So both topics have their history, and for a century or so they were independent, and now at the beginning of the 21st century these come together and there's a name clash. I'm sorry, but there's no way to avoid this. All right. So these valuation functions of the agents, they give rise to these tropical polynomials, and these are n-variate because this is about n goods, right? So what do? So I just write down all the possible. I'm maximizing. So the monomials come from these bundles that I'm interested in as agent J. And so they become exponent vectors in my multivariate tropical polynomial. And the evaluation so the valuation at that particular point, so this becomes a coefficient. All right, and then I want to maximize because I want to maximize my profit. Now, so the tropical hypersurface, but for a short moment there's no auction, right? So I only have those ingredients from the auctions, which are these functions uj. So these functions uj. So these are the only ingredients, and the sets capital A. And previously I was constructing an auction, and now I'm constructing a bunch of tropical polynomials. Of course, once I have a tropical polynomial, the first thing that I'm doing is I look at the tropical vanishing set, and this is the tropical hypersurface. So, and in my economical model here, so this is the set of prices where the agent likes at least two bundles exactly as good, right? So if there's more than one bundle which looks totally the same to the so in terms of profit to that specific agent J. Now the aggregate valuation corresponds to the product of these tropical polynomials, and the product is taken tropically, of course. And we've seen this previously. So when we talked about these hyperplane arrangements, right? So these hyperplane arrangements so corresponded to products of linear forms. And here we have a product of arbitrary polynomials of arbitrary degree. And so again, so this corresponds, the tropical hypersurface is the union of the hypersurfaces of the individual polynomials. So one for each agent, and we have n agents. And now let's look at an example. So in my example, I have two agents and two goods. And so this gives rise to these two tropical polynomials, and which are bivariate, right? So these are bivariate because I have two goods. And so this is how these things look like, right? So this I have two goods, and one is called X and one is called Y. And so then this means so the agent would value a bundle if they would get Y, so they would give it a value of +3. But if they would get two Ys, so then they would associate a value of 5. So for some reason, I already pointed this out. So the evaluations don't need to be additive. So for some reason, right, so having more Ys is somehow good for agent 1, but not, so it is important to have one Y, and two Ys is just is not twice as much as one Y, okay? So, but then there is a situation where if I have two Ys and I additionally get an X, then that is then I want to put a lot of values, so this is 9. Right, because if I have these, think particular Lego bricks. If you have two of one kind and one of another kind, so then you can build something very, very beautiful, but only if you have the combination of exactly one of them and two of the other, right? And so that's why it gets such a high value. And then the life is much simpler for agent 2. So they are interested in getting one of the goods, and they don't care which one, right? So this is the valuation function for agent 2, and there are only two agents. So how does this game continue? Well, so then you can form one tropical hypersurface, so which is a curve in the plane for agent 1, and you can form another hypersurface in the plane for also another curve in the plane for agent 2, and then the union is this thing that you see over here, and you can still see the individual curves, right? So because obviously this was a tropical line, and so this is this max tropical line. So this is the hypersurface that belongs to this guy. And this curve of degree 3, total degree 3, is the thing which belongs to the first agent, right? And you just overlay them in order to see the tropical curve defined by the product of these two polynomials. Okay.
Mikhail,
and now
just a quick question. The previous slide, there, yeah, in your game theoretic interpretation of this tropical hypersurface, so you're taking the maximum, right? So
Yeah.
Those two bundles there should be two bundles which the agent is indifferent to, but they should be maximized, right? The corresponding value. So that is also there, right?
Yeah. Well, so the thing is, in this picture. In this picture, you do not see the bundles directly because you look at price space. Right, so you do not see the lattice points. So therefore, this picture doesn't have any lattice points.
Okay.
Right, so each point in this space is a price. So this means at this price, right? So you see my mouse?
Yes.
So at this price, agent 2, so each of these regions belongs to a bundle, right? So this is a monomial of the tropical polynomial where that function is maximized, but it is only there, right? So on the hypersurface, there are at least two monomials which win at the same time. And outside the tropical hypersurface, there's always a unique monomial which wins.
Right.
Right, so this is, and there are two monomials. We will look at this in a short moment. So which win simultaneously. So this is where the second agent doesn't care if they get the bundle which belongs to this thing or to this thing. Right. And so here's something interesting, as you can see. Right, so here's a point in price space where both agents are indifferent with respect to two bundles.
Yes, two bundles. Yes.
Okay.
Okay. Thank you.
Okay. So today I would like to
Miguel, if I may,
sure.
The good space and the price space are dual to each other, right? I might be wrong.
In a way, yeah. So there of course there is some kind of duality, and let me get to that. Okay.
Okay. Thanks.
Right. So there is a duality going on. Exactly. All right. So the thing. One thing which is important about the intersection of optimization and tropical geometry is, I already pointed this out on the first day when I was talking about shortest path. So there is a lot about algorithms going on in the background. So we were touching this topic now and then. But if there are algorithms, then there's also software. And so there's a software system that I have been busy with over the last 20 years, and this is called Polymake. And today I would like to show you a little bit of that. And so I will use this example to tell you a little bit about Polymake. So therefore, I will stop this share now, and then I will show you a notebook. And so this will also be online, and so you can play with it by yourself if you want to. So I stop this share now, and I will come back with a new share in a second. Okay, so where is it? Okay. Okay, where is it? Here is it. Okay. And okay. So I hope that you can see it. And make it a little bit larger. Maybe that's better. Do you see my screen share?
Yeah, we see it.
Okay, good. All right. So the software system Polymake is an open source software system written in Perl and C++. You can download it from our webpage, but also it is designed to run on Linux and also Mac OS. So these are supported. If you happen to use a Windows computer, you can still use it through the Windows Linux subsystem. And most Linux distributions have a version of Polymake from their standard package manager. So most of the time you won't have much trouble of installing this because your package manager on Linux at least takes care of that. So we do provide bundles for Mac OS, and check out the webpage. All right, so it's a fairly comprehensive system which deals with polyhedral geometry of all kinds, but also a number of other things, including tropical geometry. And the various functions are split into applications, as we call it. And so here and so the first command that I have here, so this starts this application tropical. So there's a version of Polymake that you can run on the usual command line, but it is nicer to use this Jupyter front end, which you might know from systems like Sage or others. So this is a very convenient way of taking care of your computations and adding some additional text, including text and whatnot. All right, so now, so I start my computation, and I'm taking exactly the polynomials that I had before. And the only thing which is slightly different, so if you look at that, so these are the two tropical polynomials which come from the two agents. So maybe we look at the second polynomial first. So you see a variable w that didn't occur before. And this is just because Polymake always uses homogeneous polynomials in the tropical world. Everything is homogenized. So I had two bundles, and so referring to the x and the y coordinates. And now I need to bring in an additional coordinate for homogenization, and I choose the w because such that the pictures. So this corresponds to. So I'm picking a letter which comes before x, because then the first coordinate is my dehomogenizing coordinate for the pictures. That's why. All right. So, and then similarly, so the first polynomial was of degree 3. And so here was a 0 before. This becomes 3 times w now. And I fill in copies of w in order to make the total degree 3. All right. So this is what I do. And now I have these two tropical polynomials. I'm just checking how they look like. So in computer algebra systems, it is common not to pay too much attention to the names of the variables. So internally, these things are just, the exponents are just integer vectors. So this means whenever, so there's a way to globally change this behavior, but I want to do this locally. If I want to see my variables back again, so then I need to remember which variables I was using. But here you see the polynomials are still the polynomials. The only thing which looks a little bit different is, so this tropical polynomial now looks like an ordinary polynomial. So right, so it just remembers you that this is actually as a tropical polynomial. So this is a third power. This is not a coefficient, right? So this is a coefficient, and so this is this coefficient, and so on. All right. Now I can form these tropical hypersurfaces. So Polymake is indifferent with respect to min and max, which means you have to spell it out every single time. So this is on purpose, because you saw in the presentation yesterday, sometimes it's important to do combinations of this. And so there's you can do both things. So now T1 is the tropical hypersurface, which is given by the polynomial corresponding to the first agent, and T2 is the hypersurface for the second thing. You saw that the aggregate situation is controlled by the product of these two tropical polynomials, and this is f. And if I want to see what f looks like, so then there is this is this situation here. So now this is I have a degree 3 polynomial and a degree 1 polynomial. I multiply them, I get a polynomial of degree 4, and this is the homogeneous tropical polynomial of degree 4 that I get, and this is what it looks like. And so the situation is controlled by the tropical hypersurface, which is the union of the previous two. And this I can get now as a hypersurface of the product of these two tropical polynomials. There is a way to visualize that. Right, so there's a way to visualize it, and you will recognize the picture that I showed you before. Okay, so this is this situation. And now there was a question coming up with respect to this duality, and but maybe there are some questions. Maybe that's a good time to ask questions.
Questions? Online participants, you can type the question. I don't see any hands at the moment.
So I will put this, so on GitHub, I'm maintaining a site for Jupyter notebooks, both for the Oscar computer algebra system and for Polymake. And I will put this there, so you can check it out later if you like, and if you want to play with this and your own functions. All right, so then let's look at all the monomials that you get. So this is, so now I'm trying to get to this duality, right? So here the tropical polynomial f has a certain number of terms, right? So, and each term is a pair of a coefficient and a monomial. And the monomials are just integer vectors, right? So, and this is, I want to look at the integer vectors. And so a lot of, so Polymake internally works with respect to references to sub-objects of the individual things that I'm working with. And to this, so it is important that the monomials just are labeled. And you see, so here, so this labeling, so the function that I showed you makes this labeling just apparent. So for instance, here the first term is just w to the 4. And so therefore the first monomial here is 400. Right, so this is the monomial which corresponds to the exponent vector of 4, 0, 0 of the monomial w to the 4. And similarly, so there are the other ones. Turns out there's a total number of 9 of them. And so the first column is just the label that they get, and they are just consecutively numbered starting from 0. And now this duality is expressed in terms of the dual subdivision, right? So there's two ways how I can read the combination of integer vectors and real numbers. So either I can cook up a tropical polynomial like I did, or I can produce a height function on those points, and I look at I lift it to one dimension higher, I take the convex hull, and then I take the lower faces and project them down, and this is how I get a dual subdivision. And this is the picture that I'm getting. So now this is these integer. Now you see 9 points labeled from 0 to 8. So they correspond to these 9 points. And so you see that the convex hull, which is happens to be a pentagon, so it's a 2. Because of the homogeneity, so this lives in a hypersurface, in an affine hypersurface in 3 space. So therefore, I can rotate it in 3 space if I wish. And so I get these 9 points and the subdivision, which is dual to this thing that we saw before. Just to give you one idea. So for instance, look at so there's only one interior lattice point of the pentagon which is actually used in this subdivision. So this is another interior lattice point that is not used. We will come back to this point later. So, but this is the only interior lattice point here which is used, which occurs as a vertex of cells in the subdivision. And so this is exactly dual to this central pentagonal cell. Right, so this has 1, 2, 3, 4, 5 vertices, and this is dual to the 1, 2, 3, 4, 5 two-dimensional cells, which have the lattice point number 5 as a vertex. Right, so this is So this means that the monomial which maximizes this thing here. So this is the monomial 1, 1, 2. So this is this situation, and this is how you can analyze this thing. There are many more things that you can do. I don't want to give a full polymake demo today, but I just wanted to bring across, if you want to do these things for your own data, there is software and that is available and you can use it. Okay. Now again, question for polymake, or I go back to my presentation. I don't want to change too often because this always takes an amount of time, as you see.
Questions?
Okay, so then I stop my share again, and I'll come back to my other share. Okay. Okay. Do you see my screen again?
Yes, yeah, we see your slides.
Okay, good. So this is where we left off, and now you saw how you could compute this. And so, and for instance, you could see that 1, 1, 2. So that is the so this maximizes everything here. So this is what we just saw. All right, let's continue. So here's a little bit of a background of what is going on. It is not very difficult, but it is important to understand, right? So if you have classical polynomials, then you can tropicalize them with respect to the order function or valuation function to get tropical things, and then you can translate this into the tropical geometry. So this D is an unbounded polyhedron that I usually call the dome, right? So this is the unbounded polyhedron in the space 1 dimension higher from which you project in order to get the regular subdivision. And so this is the regular subdivision in a piecewise linear embedding in a space 1 dimension higher. This is exactly the boundary of this polytope, so the polyhedron. So this is this shape here. So you have a map, you have a lot of maps. So if you have an honest polynomial of a Puiseux series, you can tropicalize, and then you can dualize. So this is this dualization. And then there's another way. If you have a polynomial and a second polynomial, you can form the product, and then the varieties are embedded. The same thing holds tropically, and so you can also analyze what happens to your polyhedral geometry, to the unbounded polyhedra, these domes you're constructing. And the essence of this proposition is that this diagram, which allows you to go in all possible ways along the arrows, so this is commutative, and this is crucial for the analysis of this things. And the mappings are given explicitly, except for this top row, and these are just usual embeddings. So these are just usual embeddings. Okay. Now, so the key question in my economical situation is the question: when does this competitive equilibrium exist? So remember, so this is the situation where everybody is happy because everybody can maximize their profit. All right. So before we go to the general result, let's look at a simple case. So if the valuations are constant, right? So just imagine so this means that each agent just picks a number of bundles that they are content with. And the actual, so there's no difference for the agent among these bundles. So they're like everybody equally good, right? So, and this is true for all the agents. So this is kind of, so then the actual data that you have, so the actual values are not so interesting. So it is just picking bundles that the agents like. So we are talking about subset, integer, finite sets of integer points in R to the n. And so then the competitive equilibrium exists at a certain point A, which is a lattice point inside the convex hull of the aggregate, so Minkowski sum of all the AJ, if and only if that particular A is contained in the Minkowski sum of the individual sets AJ. So if this can be written, if A can be written as a sum of elements of the individual sets AJ. Okay, so this is just a, and so now it actually turns out that even the case for a single good is interesting. So I still have m agents and one good. And but now if the evaluation is not constant, so again, I have these n bidders and I have one good that they're competing for, and then checking if the competitive equilibrium exists at a given point A. So this amounts to the question, if among the I have some subset of lattice points from the agents. And then the question is, can I? Is there a selection of those integer? So the lattice points are just integer numbers because I only have a single good. And then the question is, so for that number A, can I pick a subset of the given numbers such that A is a sum of those? And this is a subset sum problem. Known in theoretical computer science, and this is known to be NP complete. So that is a hard problem. So this means even for one good, it is algorithmically difficult to decide if competitive equilibrium exists at a given point. Let me repeat that. So we're talking about an economics problem, and it turns out, so we want to, so the auctioneer organizes the auction in a way, wants to organize the auction in a way such that social welfare is maximized. But even if there's a single good, achieving this goal is computationally hard. This is what this says. Okay. So now imagine if we have more goods, then it is even harder. So therefore, it is desirable to know something about these competitive equilibria, and so every theoretical result about them is interesting. So here's an exercise for you. So the first interesting case beyond the two that I mentioned is obviously the one where I have m and n equals 2. So I have two bidders and two goods. And then the exercise is to show that there are point sets. So these are finite point sets in Z2, such that no competitive equilibrium exists, no matter which utility functions are used. So it is, so competitive equilibrium doesn't come for free. So sometimes you need to, it is computationally hard to check if competitive equilibrium exists. And sometimes there's no hope at all, because it just does not exist, no matter what the opinions of the individual bidders are. Okay, this is the take home from this slide. Now, here's a lemma. Now again, we are in the general situation, m agents and goods, and we have the individual valuation functions of the m agents and the support sets. So these are the bundles that these agents are considering, and these U functions, they keep track which bundle is liked to what extent. And again, we have the capital U and the capital A, which are the aggregate versions of the two of them. And then the following is true. So if we look at the aggregate tropical polynomial, which is the tropical product of the individual tropical polynomials, then we have the tropical hypersurfaces, the union. This is what we already saw. The demand, the aggregate demand is the sum for the Minkowski sum of the individual demand sets, and then competitive equilibrium exists at A if and only if the pair A comma price of A multiplied, so scalar product with A. So the pair, so A is a vector in R to the n, and P times A is a real number. So the whole thing is a vector in with n+1 coordinates. This lies in the boundary of the dome of F, right? So this is the statement. So competitive equilibrium exists at A if and only if the point A comma PA lies in the boundary of the dome, right? So and if you look at this in the dual setting, so this competitive equilibrium exists if and only if the point A is actually occurs as in a cell of the dual subdivision. Okay. So we will see this again in a second. And so now here we are heading towards the key result in this topic. So this is the unimodularity theorem. And so a vector is called primitive if, so we're talking about lattice points in lattice vectors in Z to the n, if the greatest common divisor of the coefficients of that vector is 1. Right, so geometrically, this means if I'm looking at the vector d, and I look at the ray r times d, so this is also the ray emanating from the origin into the direction d, and then I take the entire ray, then d is the first lattice point on that ray if I start looking from the origin. So this is an if and only if, and the set d in z. So this is z to the n, sorry. So there's an exponent message. So a set d in z to the n is unimodular if for each r basis in d, the z span is the entire is z to the n. And now I take a primitive set in z to the n. So this means each vector in d is primitive. And I take AJs, so one for each bidder arbitrary. So again, the bidders are allowed to pick their bundles that they like. And then I'm saying a valuation, so this again depends on the bidder, is of demand type D if every edge of the subdivision dual to the tropical hypersurface induced by U is parallel to some vector in D. And conversely, each such vector in D occurs. Okay, so this, and then if I have that, so then here's this theorem. Every collection of concave valuation functions, so right, so I have these piecewise linear functions which are which come from the maximization. So this is of demand type D. If they are of demand type D, so then they have competitive equilibrium if and only if the set D is a unimodular set. So this is this thing. And now I would like to go back to my polymake thing again. So I'm unsharing this again. Let's stop this share. And I'm sharing the other thing again. So this means in this situation that I had here, right? So the situation is the following. So the aggregate demand is encoded in the bundles that I get as sum of the existing bundles. And so these are all the lattice points that I see here. So these are all the monomials that occur in the product of these two tropical polynomials in my set. So I have nine bundles which are of interest. So 9 ways of selling, 9 ways of combinations of my two goods that I'm considering. And so all of the 9 lattice points occur in this subdivision, except for the point 3. So the point 3 does not occur in any of these cells as a vertex, right? So this means I have this dome, so you need to imagine. So there's a 3-dimensional polyhedron which is spanned above this set that you see here. So everything is raised to a 3rd coordinate, and the 3rd coordinate is given by the coefficient. And now, all these things that you see here correspond to faces on the boundary of this unbounded polyhedron, but nothing near the point number 3, because the coefficient for 3 is so low that it cannot reach the boundary, right? So that's why 3 doesn't occur in the subdivision. This means social welfare cannot be attained at 3, but it can be attained at the other points. This means the competitive equilibrium in this example exists at 8 out of the 9 points, all of them except for 3. Okay, so I can. So this means for each of these, for each of 8 out of 9 points, I can find prices such that I can make everybody happy, but not for this choice, right? So in this 3rd thing, so this was 2, 1, 1. So this is the homogenizing coordinate. So the only thing which does not lead to a solution which makes everybody happy is one x and one y. 1 x and 1 y does not make agent 1 and agent 2 simultaneously happy, no matter which price I'm asking for. Okay, so this is the outcome of this analysis, and this is the content of this theorem. And so this kind of is only the beginning into a long story about these types of auctions and other auctions. And this is this result of Baldwin and Klemperer, which has a somewhat tangled history. So I think it was first announced in 2013, and then there were proofs appearing on the internet. The whole publication process took a while, and but there I should also point out that the version that how I'm presenting this. So this is based on a paper of Ngoc Tran and Josephine Yu. So they also discuss further connections of this theorem to toric geometry, in particular Oda's conjecture and other things. So it's a very interesting paper that I recommend you to read. But I should also point out so that not in this particular language, but so the geometric core of this theorem is a much older idea. And so there's a 20-year-old paper by Danilov, Koshevoy, and Murota, which essentially says the same. And since then, there have been other authors who all independently also thought about these kinds of things. And so all of this is interesting to read, and there's more research to be done along these lines. But so the take home is well, these things are interesting, but so these competitive equilibria are computationally super difficult to find. So this is and there's kind of a geometric reason why this should be difficult, and an algorithmic reason due to this NP completeness result, even for a single item. Okay, so this is what I wanted to share for today. So here are the references: Baldwin, Klemperer, Danilov, Koshevoy, and Murota. So there's a whole theory written up under the title of discrete convex analysis. So there's a book by Katsuo Murota under this title, and with lots of applications to economy. Again, I have a short account of this in my book. But so if you're really interested in the geometric interpretation of so you should read the paper by Nock and Josephine. So this is what I can say about this. And now let me take one more slide to wrap up this entire sequence of lectures. So I try to give you an overview of several topics which occur in optimization. So I chose topics which are interesting in optimization for its own sake. So in the first example, so these were parameterized shortest path problems, which are relevant for network optimization problems. And so they came about from naively looking at just tropical arithmetic, and then replacing just the standard tropical sigma ring by the sigma ring of tropical polynomials, and then standard algorithms for optimization can be extended to much wider range, namely to solve such parameterized optimization problems, essentially without additional cost in a certain way in a certain regime. And then there's a general question about complexity status of certain algorithmic problems in theoretical computer science, most notably. So there's the mean payoff games, so which have this status that deciding if someone wins in a mean payoff game, that this is a problem in NP intersection co-NP, but there's no polynomial time algorithm known. It has a natural interpretation as a feasibility problem in tropical linear programming. And tropical linear programming can be used to study the complexity of classical linear programming, where there's this major open problem known as Mail-Snide problem, which asks if there is a strongly polynomial algorithm for linear programming, yes or no. Then the third thing was tropical convexity. So the combinatorial theory of tropical convexity introduced by Develin and Sturmfels. And they kind of provide the geometric combinatorial underpinnings of these tropical polyhedra, which already occur in the tropical linear programming world. But also they have a lot of other applications. For instance, I talked about this Fermat-Weber problem and the construction of consensus trees in phylogenetics. And today you saw just the tip of the iceberg of the connection of tropical geometry to auction theory. And I already pointed out that there are many, many more things. But each lecture series needs to stop somewhere. And so this particular one, I guess, stops now. Thank you for your attention.
Thank you so much, Michael. We have time for questions.
Thank you for the talk. I just wanted to understand if there are open lines of inquiry along the lines of product mix auctions based on your vantage point as you see the field today. Open problems.
It depends on your point of view. So in this. So the biggest open problem in the context of product mix auctions is a geometric one. So this is Oda's conjecture, so in toric geometry. So this talks about a smooth, resolution of singularities of toric varieties. And so understanding Oda's conjecture, kind of, and so this is a long-standing open problem in toric geometry for more than 20 years. So this is kind of, it's directly related to understanding these product mix auctions. And so the details of the connection are written up in the paper that I mentioned. So this one, the final one, by Nock and Josephine. So this is, if you want to work along these lines, so then you should think about Oda's conjecture. And this is it's a known hard problem in algebraic geometry, which allows to write, it can be studied through polytopes and lattice points, and so there's more than one way. And so, but you can think this there's various ways to think about this. So you can think of the order conjecture. If you think this is very, very hard, so then you could say this is a stumbling block on further understanding product mix auctions. But you can also see, well, product mix auctions are a way to think about orders conjecture. And then and then this maybe gives you some leverage on this conjecture. In particular, so the most interesting thing there would be it is known that orders conjecture has a solution in special cases, and product mix auctions might provide additional sets of situations where you have a positive resolution of orders conjecture. And so this, if you want to work on these things, that I think for people with a knack for geometry, then that could be interesting. Analyzing product mix auctions where you can guarantee that competitive equilibrium exists. So, and writing down large numbers of families of these things, and studying the connection to orders conjecture. So this is you can turn this into like a research program, right? So, and that is, if you want to become famous, that's one way.
Thank you for the talks.
Right.
So are you suggesting that in much the same way as physics has been applied to come up with interesting mathematics, you can use intuition from economics to try to understand questions in algebraic geometry? Is that,
Yes, actually. So I mean, Bernd Sturmfeld has been saying this more than once. So that to him, biology plays the role for mathematics in the 21st century, like physics did for the mathematics of the 20th century. And but I would like to extend this. It's not only biology which comes in, for instance, in this for these consensus tree problems, but also economy. So yes, both biology and economy are very amenable to techniques from tropical geometry, and due to the connection between tropical geometry and classical algebraic geometry, there's a lot to learn in all possible directions. Absolutely.
Fascinating direction to pursue.
Yes.
More questions? Yeah.
So in this version, the price is kept constant. So are there versions of finding equilibrium where the price point is optimized?
So yes, I mean, obviously there are thousands of concepts for auctions, and so sometimes the auctioneer just wants to maximize the price. And then you can see there are similarly looking scenarios for where people are looking at different goals. But so in this setup, so this situation is, so the auctioneer wants to maximize social welfare. Everybody should be happy. So if you change the scenario, then what happens is typically the ingredients look the same at the beginning, but then the math problem becomes very, very, very different. So it's yes, all these things exist, but they look at like similar at the beginning, but then these topics diverge very quickly.
And for the subdivision, just to recall, what exactly was the height function in terms of the price, that subdivision that we had in the example?
Okay, let's go back to the example. Right, so the height function, right? So these are the coefficients in the tropical polynomials. They come from the individual valuations of the bidders, okay. Right? So the three means for the bundle where I get one copy of Y and 0 copies of X, agent 1 thinks the value of this bundle to him or her is 3. Okay, so these numbers only occur implicitly in the construction of the hypersurface. Yes, and then from the regular subdivision, and then projected down. Right, so these occur. This dome has an inequality description where these the integer vectors are just facet normal vectors, and then they are kind of distance. So questions on how far I push out along into the y direction, and similarly for the other ones. And then I get an unbounded polyhedron, and I project it down. And here I only see the projected picture. That's why the coefficient 3 occurs here implicitly in this picture, right? So, and in the subdivision picture, this is the height at the point with coordinates, homogeneous coordinates 0, 0, 1.
Thanks.
So one comment about general auctions is that when you're trying to find an equilibrium, I think you want an efficient system, but most auction systems are geared towards maximizing auctioneer's profit, which is a different problem altogether.
Absolutely.
And I think the problem that you alluded to today is the equilibrium, wherein the fairness of the people who are bidding at the same time, auctioneer who is trying to maximize, there is some level of balance to both of them. That's a problem you alluded to, right? Yeah.
Yes,
just
exactly.
Yeah,
exactly. So typically the profit maximization for the auctioneer, again, there are several different scenarios to consider. And typically these things are less difficult computationally than this social welfare situation that I'm aiming for. So this is, you could see, well, our world is in such a poor state because it is very, very hard to make everybody happen simultaneously. And so today you saw a mathematical reason for that. Okay, so this is one way of talking about the poor state of our planet.
Further questions, online participants?
This unimodularity theorem, the condition there, can you please go there? The unimodularity theorem. So there, so the first implication, the first statement there. So you're interested in every collection of concave valuation functions of demand type D having computative equilibrium. So so I mean, one can also look at, for instance, just for the existence of one valuation function. Is this more natural, or how does that come about?
Well, so okay. Before I answer your question, of course you can answer this, talk about this other problem. And indeed, if you know the valuation functions, it's easier. If you know the valuation functions, then you can do the thing that I did with polymake, right? You do the computation, you look at all the lattice points, you check the conditions. It's computationally not cheap because there are convex Hull computations and other things involved, but that is doable in practice. So this is the natural formulation from the system perspective, right? So you want to achieve social welfare without knowing what the individual valuations of the agents are. So therefore, there's every collection of these functions. So this is the thing that you, as a politician, you want to do, because you don't want to ask every single inhabitant of India before you come up with your law.
Right. Yeah. Okay. Exactly. Yeah. Something that I was looking for. Yeah. Thank you. Thank you so much.
I think one final comment, the broader problem that Klemperer and Elizabeth deal in their paper is essentially aggregation of demands. Let's suppose there are a bunch of auctions, you want to aggregate them. This provides like an amenable language to aggregate demand, so to speak, from different auctions. Yeah, just a comment, thanks.
Questions from the online audience? Audiovisual team, please enable online audience to unmute themselves. Meanwhile, any further questions from the room? Okay, if there are no more questions, let's thank Michael again for a wonderful, inspiring series of lectures.
My pleasure. Thanks for the invitation. And I'm really sorry that I couldn't be with you in person. And I hope that it worked over several thousand kilometers of a distance.
Thank you. Thank you so much.
My pleasure. Bye.
Thank you so much, Mikhail. Thank you so much. Bye.